Hello, my name is Kalle Launiala and I welcome you to watch this part 1 of the presentation of the ball and service operating system running on Windows Azure. About the presentation, the part 1 will consist of parts of what is the ball and service operating system platform about, service operating system design, logical architecture of how it was designed, service operating system design at the implementation level of the building blocks and of the paradigm of master information versus traditional relations, and then coming together with a demo of platform actually executing on Windows Azure. The presentation part 2 that will be videoed on separately will start with the developer getting started from scratch with git clone, build, debug and deploy on the developer workstation and developer emulator system. Then we dive more into plain HTML and jQuery browser-side templates on the ball, and also revisit the web and worker role responsibilities and Azure building blocks of the basic principles of Azure. And then to the ball architecture overview and deep dive, looking at the Visual Studio of different implementation constructs that we used to build the ball on Azure. So what is the platform? The ball service operating system about the whole package running on the Azure and the size of the scope. Basically, this presentation covers all the aspects of building full digital services and applications actually coming from a software factory running on Azure. So while we focus on some areas to simple looking web development, the components and the ADM automation will provide backend and also client-side proxies to a whole network of mobile apps and embedded systems alongside with the mobile. There are parts for public repository libraries, but those we are not covering in this presentation. However, they are in the background, so we kind of explain some parts of how they can be achieved with the service operating system that we now present. One additional aspect of the ADM should be mentioned here. We speak about genuine native cross-platform implementations. So basically all the technologies that are listed here as an example for any mobile native from the Windows Phone, but also through the Android and iOS without any additional third-party frameworks or libraries will be possible. Node.js, Java, PHP, Python, all these apply because ADM makes the cross-platform native through very simple T4 generators. That we won't dive into this presentation much, but that's something that is unique compared to other kind of cross-platform solutions currently available. So what is it then? It's basically, in the simplest form, it's a publishing system for authorized information, web content, any digital content, and most importantly, digital application and service development and integration enabler platform. It is kind of a SharePoint and BitStalk and IIS even bundled together. It's at the primitive level, so it comes from the level of the IIS, but it provides the functionality of what you've used to see from the SharePoint-based solutions and the BitStalk-based solutions. And how do you install it then? It's you don't install anything. It's you deploy your software stack and run it. And of course, yeah, any open source software stack could say this, but the amount of software you deploy when you deploy the whole service operating system is relatively small compared to the functionality. It's just a series of connected reference architectures that make the system run. So diving a bit about the acronyms, the ball and service operating system and how they relate to each other. The ball is basically fundamental core. It's originated from information models for storing and processing information, which also then include the process models as well. It's a context insensitive, it's kind of a shapeshifter. It doesn't constrain anything you put in or process, not even it doesn't require authentication necessarily or authorization as is. So therefore, we also introduced the SOS to take care of the real world needs and constraints. The SOS meaning the service operating system. That one basically provides practical authorization layers that we designed to map on real world users. It's kind of context sensitive and context insensitive. Basically context sensitive in a way that it enforces certain design constructs to be there so that the systems built on top of it can rely them to be there. But basically all the content and all the information that you process in it is completely content insensitive in that kind of way. Then ADM was already mentioned in the 2 slides before. It comes from abstraction design methodology. It basically in this context enables mainstream developer to pull off the above, to work with the ball and with the service operating system. Basically it's a XML and T4 based method that works as is on Visual Studio. I held a presentation on last year's Tech Days that where the full material of that starting from scratch is available on our tech blog. So I won't dive much deeper on the ADM in these presentations. So briefly about the ball. I'll run a quick visualization of it. This is not the ball, this is information. And information is stored in somewhere and recalled somewhere, so we need kind of a database. This is, in this example, an atom, and it's executable code, smallest unit of executable. So atom could be, for instance, an OK button. Different kind of atoms would represent the different kind of UI controls here. And combining the atoms together, we get something that we call a module. So basically, a module is a form, a visible form in this example. It applies for the business logic as well. We'll dive a bit deeper, a bit better on that example later on. And so combining the modules together, considering that it can be any code, we get an instance. Instance can be configured how it's built on the modules, but it's something that we think of full-blown application, such as a mobile app, or in this example, for instance, a full website app. Entering user to the picture, user experiences the instance in through different interfaces, a full-blown desktop application or a mobile device or a tablet PC. So basically users enter input to the system, and if we take ourselves a bit out of traditional application level silos, we can think of that users interacting with any system, entering their own data in, they can get the feedback to different devices as well. Well, easiest practical example is that using Samsung or iPhone to guide the TV, smart TV, is this kind of example, or just a traditional TV remote control. You actually operate different device than where you get the target information. I mean, where you receive the information then onwards out. So this is what we call the ball. It consists of information presented to the user through the interface and the actual software stack ending at the instance of that are combinations of apps and services. So this is what we mean as the ball, as a combination of multiple services, multiple apps, basically whole digital system provided to the users. And now we don't want to picture the whole world as the ball, although it could be, but it becomes more relevant if we think of it a bit smaller scope, that we can think that the world is actually consisting of multiple instances of the ball running on different systems. So while the picture before thought as a ball as something that would bring together different services, while that's true, when applying the real world services, it's easier to think of that every single app or service can be seen as a small instance of a ball that's available to be cross-connected with the other instances. Then, based on this abstract illustration, how about some kind of reality check? How does the ball apply for today's technology and business? Well, it's available to clone from the GitHub. So basically, the command series of git clone from the abstraction dev / the ball on Azure gives you a folder where you can go get the update to the project and see from the README. We'll demonstrate better on the part 2 of the session or the videos to how you can really start from the scratch. So this is something you can run starting today. Where does it apply and accelerate? Well, basically because it's a core level information management, but controlled with the reference architecture, it applies on every main aspect of the IT and ICT systems available today, starting from the software development services, because we run it right now on the Azure and Visual Studio, reaching to information management and collaboration. That's when we can demonstrate on what we have currently built on top of it as a service operating system. Very seamless transition to system integration services, and especially on master data management. Then business process wise, we can look at it as enterprise architecture level with the twist of that we can automate everything out of it. And then entering the mobile app space, any kind of mobile worker solution comes to the picture as well. In comparison to what's there right now already with the mature and modern code generation aspects, the ADM brings the automation in a maintained way to the picture. It basically means that building and maintaining, kind of building onwards on top of the ball, consists of cycle of following things. Semantic information models define what we run on the system. Logical business operation combined with that tell how we modify the system of the information in the system, and then integration interfaces and contracts declare how we make the processes callable and cross-connect the systems, applications and services within one system, and also reach the other systems. And basically, this is continuous workflow operated in Visual Studio 2012 and Windows Azure, and that's how the ADM can power up this whole continuous life cycle of maintenance and supporting automation. Then we dive a bit to the service operating system design, so the logical constraints on top of the ball that make the SOS a practical, real-world takeoff. Logical architecture is, in this context, the constraints given and design-wise chosen how they should be applied. We focused on reflecting real-world practices and real-world of today to give the constraints, and also taking into account the technical constraints of how software is built today, what kind of architectures are used, and most importantly, what drive to choose certain kind of architecture. So what are the elements that we need to mm, honor when we build a software architecture? This is a generic application architecture. It doesn't in a way focus on how many tiers we need, but color wise we've underlined the areas that differ and that kind of set the boundaries for the architecture. The green area is something that we can trust completely. We can trust we have full control of the information models and processing and validation on that area. The yellow one is user interface. That traditionally cannot be trusted because we have no control on what the user in the end will run on his or her device. We just see it through our service interface. So we cannot completely trust that area, but we of course have to trust it on providing information to our system. Then the blue area is here separated as something in between. It's a trustable service integration area where we kind of trust either external data that we get or external services, but we cannot rely on it complying to our business validation rules, nor we don't have a control to make the modifications on that area. So that's a kind of separate in between area that we have to take special cautions to accept the data coming in. If we look at this architectural block as reference architectures, I've written it out in the block boxes I won't read now, but basically ADM allows us to take control of every single part in the picture. And in the coming in the few slides onwards, when we start to speak about the implementation layer, we reduce the traditional N-tier level to comply with these kinds of areas in a very simple manner. Then the other aspect that we chose to have the constraints in is we focused on real-world collaboration, roles and emails. Basically, people always act as a role, and people collaborate with other people because of their and the other people's role. So the decisions are always made with people acting in a certain role in a process. Then people trust emails. Emails actually in the recently they have been claimed as a in a court case valid proofs, even though technically they are not necessarily trustable or completely secure, but basically people trust emails. Today's business contracts are validated. The changes on contracts are made in the emails. And what SOS does, it enables the above constraints to be digitally accelerated while still offering a transparent fallback to non-digital world to the emails and the roles, so that it's kind of straightforward to accept the acceleration of software having these components. Then one additional constraint that goes with the slides before is that information is always owned. Information has always owner. And in this term, we don't mean as a copyright holder that somebody who really legally owns the information. However, copyright holder is one owner. By this owner, we mean something that every person is when he or she receives an information. Basically, if I receive a paper that's completely confidential, for instance, or it's a complete copyright of a book, I still kind of authorize the further use and distribution of that information. So if I decide to share the book or give it onwards, that's my decision to make, and that's why what we mean that I own the information. And in this context, privacy aspect is also critical. So focusing on privacy aspect, real-world case of smart traffic privacy issues. The red dot here represents kind of privacy or confidential information problem. This is refined from a Finnish Ministry of Transportation and Communications, who were examining the way to make a taxation based on GPS data of an individual. And on that information flow, we kind of can identify the critical problem in a kind of modern democracy if somebody knows the combination of who and where of any individual. Adding when, I mean this problem is critical. Often the component when is also in the picture, which makes the problem even more critical. And the only solution that can solve this kind of issue that actually applies on all the Internet of Things is that we can guarantee the separation of the information. So only way to solve this is to have an auditable position, auditable place that the separation really happens and the who and the where are separated in the picture. Here is the same picture again, basically underlining that it applies everywhere. So if we have a smartphone or GPS device providing that information, even though it's not, even if it's not today used onwards, the information that's available somewhere makes it kind of a critical problem. And the separation itself, it needs to run on some server system. So basically we have scenarioed how the ball and SOS can solve this problem by providing transparent means to audit the actual software stack that does the separation. Okay, then we dive into the actual practical design of the SOS. So the implementation decisions we took to actually make it real and run. So taking focus on the roles and emails, we chose a solution that separates the authentication completely from the authorization scheme. And by that we use the technical authentication coming from the OpenID providers, OAuth providers, possibly even strong at the bank authentication level. And we separated it from the trust token of being the actual email. So the system actually validates the email of a certain of any user an account, and then the actual collaboration happens and is authorized by trusting the email. So collaboration groups invite email to the group. If at any stage the system invalidates the email by itself because the user didn't validate some recently sent confirmation to the email, or if the user himself or herself removes the email to the system, all the authorization and memberships of the groups are invalidated until the email address is again validated. So it falls back to the principle that if you would trust certain email address to be your associate or partner, then you can trust it coming from the system as well. And there are schemes where we use different kind of authorization, but this is very down the level practical that applies where the current cloud software providers of bigger ones just like Facebook and LinkedIn apply as well. And in this picture we also have underlined that the ball can actually run on premises as well. But here we focus mostly on the Azure because of the huge scalability and big picture benefits. This is another more detailed picture of authorization contexts. So when groups trust a user with the email, we wrap up a security context that where the information is always processed within the context, and it requires specific actions to move the information outside the context. Basically all the accounts have their own contexts and the groups have their own separate contexts. Then the blue box here is something that I won't go in much deeper in this session, but it's an implicit fact that we recognize that every collaboration group does its work so that it could publish the results in some form. In this current example, or sorry, current implementation, we recognize that some area of the is completely public, so it doesn't require any authentication or login information to be accessed. All the information in here applies to traditional documents, but also on binary and media data, and also actually on applications and services that are run within the security context. So actual functionality can be thought as a component of this picture as well. This is another example of a cross-collaborational process. We had a scenario where embedded system provider needed to have the whole system audited for safety regulations in EU machine directive. So in this picture, the customer who is purchasing the whole system is the guy in the middle of the blue guy in the center of the screen. The left side is the internal process of the embedded system provider that shares certain amount of information with the customer so that the customer can onwards share the information with the external auditor that guarantees or verifies that the system is audited. And this kind of process is really heavy to do manually, so its whole key value is that the modifications of the system then can be audited just for the parts that have been modified. And in here, the security boundaries are kind of illustrated with the colors. So the internal process doesn't have to have anything to do with the external process of auditor, but the customer needs to have the information, only that part of information available to play in the role. So drilling down the relevance of what we presented so far in context of this also, users want unified experience based on the interface, not on the application. So if they use the certain platform or certain technology tablet, for instance Windows 8, they expect it to behave like a Windows 8 behaves. If they use the iPad or Android tablets, they still want them to be like they expect the Android or iPad tablet to behave. Application and services are to serve to kind of do the job for the user. So the focus should be on usability and not on the bling bling, kind of that looking good but being confusing. And when we start to focus on these kinds of things, we soon realize that applications need only a fraction of information to operate on their part. And some of the modern architectures, for instance in Android, already have some components that behave like this, but they are not explicitly enough described or made available through libraries so that they could be relied on or trust to be audited in a controlled manner. So we kind of bring this kind of a solution to more generic use and regardless of the today's platform, so it doesn't have to be Android at all. Now then, let's focus more on cross-connecting anything, diving into the service layer. So on the client and service layer. Basically, service interface definitions can be thought of like a pseudo-language method call. So they have a return value, they have a method name, and they have the parameters. Of course, with the technical parts as well, so that if it's a date time, it needs to be there as well. And this is something that we can easily accept because executing code always knows what to call and from where. And basically, within the programs, we have a current object-oriented way of saying that we have a customer. Basically, if our app has a customer and some other app has the customer as well, they are never the same. So the semantics, although it's not explicitly defined, they actually apply in reality. Here is a better image of client-server or server-to-server interfaces. So whenever we use this kind of service, for instance with Windows Communication Foundation, there is always the interface agreed with the client and the server. And if we think of it as an abstract thing, abstract definition, it doesn't necessarily need the network stack to be called. So we can consider a caller and callee, or service server and the client, to be in the most effective way a method call that's where somebody calls the actual implementation within same process. It kind of provides the service to the caller still, so we can kind of use the same model even if we leave out the network in the program, in the picture. So then if we use another example of actual concrete infrastructure, modern cloud infrastructure, we can bring the picture of a service bus, for instance from the Azure service bus, which has some kind of queue storage for the messaging, so that it can be thought as a reliable channel even though either of the parties would be offline during the call. The relevant part here is the service call between the device, in this example between the tablet and the web-facing server, the actual communication call that transmits the information between the parties. If we focus on that, we can look at the distributed architecture way as well. Focusing on the service call, we can implement the service bus also in a reference architectural blocks in the client side and on the in the server side, without having any concrete service bus there at all. Basically, we can also have a kind of a hybrid. So we have the reference architecture and it still takes advantage of the actual Azure queue or a service bus, but also can take advantage of the blob storage and other components. If we have this kind of distributed reference architecture where we get rid of the whole service bus, we kind of lose the ability to be offline and still have other party online and messages traversing through. However, if we are running our web-facing server or the ball already on the Azure cloud, we can kind of guarantee that that part of reference architecture that has the queuing component will be staying online even if we take the backend of our own backend occasionally offline. So basically we can still have exactly same features that the actual service bus, but having the additional advantage that if we bring in the Internet of Things kind of embedded systems where sometimes even the HTTP stack can be really difficult to implement, but the TCP IP level stack is already available, we kind of simplify the whole solution and open whole new possibilities and still get the same benefits, exact benefits of if we had a actual service bus running. Now, considering the services and introducing the authorization to it, if we take an analog to actual mobile apps that run on mobile devices, they are all separated in a way that the user during the installation gives the app the rights to, for instance, access network, access local GPS thing, and so forth. So in here we take that one a bit onwards further, the analog, and we introduce a way that app actually is providing some functionality and it's consuming some to provide the functionality. For instance, some kind of map app will be consuming the GPS signal, so it needs the authorization to do that, and then it provides some rich information on top of the locations. And if we use the same kind of model, but accept the fact that we can digitally take advantage of that and not necessarily have it separate silos, we can kind of think of app-to-app integration, so really small component integration. And it of course applies between the services. But this is within the owner account or a group secured context. So in here we kind of cut off the possibilities for the apps to call home, so they never get a network. They just get input information of semantic form, and they provide output information that can be then fed to other system or to be rendered on the UI. This is the bigger picture of the same thing. I won't go this much through, but basically cross-connecting digital services and then having publicly available context or content or open directories of where to fetch which services, we get to the earlier presented Lego kind of module experience where people can trust that the system doesn't leak information, but they get whole kind of custom functionality completely audited and transparent and safe to run on their security contexts. Okay, then how we can discover the services. So if we present that kind of models, how do we pull it off that we can discover the services and match the consumer and provider model? Information, if we bring it to not even that fundamental, but kind of concrete level context, it's the real world. So if we can think of even manual process like ordering a pizza in the same kind of thing that digitally automated process. So if we have a ongoing negotiations with a pizza sales guy on the pizza restaurant, it's exactly the same amount of information that we need to transfer from us to the salesperson that we do on the online pizza service. So we agree on what kind of pizza, then we pay, and then we receive the pizza. So basically this is more than a kind of loose analogy. It's information wise, that's exactly what gets transferred between us and the service providing, in this case a pizza providing service. Another example, bringing it to the real world, is real world service discovery. There is a service called Kaloom that makes these kinds of things on location-based services and drilling down the real world, real people required services and looking and providing services. So kind of a service marketplace. Taking the human aspect is give us a good example of how we can actually agree of provided and consumed service in a really effective manner. So this example is in Finnish, but I'll translate it on the fly. It's using the daycare examples for children, such as childcare or parental network kind of services. And when humans agree or speak within the context, one word such as I need my child to be taken care of for 2 hours when I go to massage, for instance, few words explain it completely to somebody who's providing a childcare services, daycare services for children. And if we map this to it basically means that we are speaking something about semantic information matching. So coming back to the example of accepting the fact that there is always implicit semantics. So if we have a customer in my app and customer on some other app, they somehow, the names of the classes already imply that these are at least trying to be something of similar of a kind. And basically if we would be integrating systems that call something a customer, we kind of need to do semantic mapping. So then we need more details of what my customer means exactly and what the other customer means. So technical way, we can solve this in a way that we bring back the technical signature of a service method, which includes the technical return value, method name and parameters, and then we introduce additional information layer, kind of semantic namespace to each of the components. So if um, get my customer record would be the service name, and it would return a customer. Now if we introduce a semantic namespace to it, it would be kind of myapp.customer provided from myapp.get my customer record, and then the parameters would be myapp.social security number, for instance. Now this kind of signature would be complete in a kind of information-wise, which means that we can actually calculate a unique hash out of it for to be matched of exactly same kind of signatures to be provided, so that we can actually have multiple services, different services, but providing the same service to outside consumers, and then the consumers can of course then be searching for the same hash value. And in addition to be exact match, when we recognize that we have this kind of matching service interfaces, then there can be different tiny services that map the information between, so that they create from my customer to your customer. And if we build a compatible chain of services, if somebody is consuming a service that needs my customer, and what's being provided currently is your customer, providing a mapping that gets from your customer to my customer can establish a full chain of pluggable interfaces and therefore pluggable services to be executed. Bringing this back to the real world context, there is ETLA, it's an economical research agency in Finland, who made a really interesting and a bit more than an interesting practical project where they tracked down the real world nurses moving in the real world hospital using Bluetooth beacons and a smartphone Bluetooth to see in which room they are. Okay, they used also accelerating meters and GPS to track down the movements. And what they got out of was real world processes of real world nurses. And they also kind of pretty soon figured out, and it's completely different processes that these external IT or information consultants, EA, enterprise architecture consultants, made out of their illustration of how the hospital works. And well, if you track down real world nurses, I would say that that's the real world, and then the artificial processes, if they don't comply with that one, it's not, there is no argument of or disagreement of who is right and who is wrong. And basically this is when we do this service design flexible enough, we can reach to this real world nurse processes and really completely ditch the artificial consultant made processes. Here's the link to the ETLA's process. The material is mostly in Finnish, but if somebody is interested, please contact me, for instance, directly, and I map you with the ETLA guys on the hospital processes. So then the building blocks of SOS design. And now we start to come to really simplistic. So we have the relevant interface to real world users. Then in the picture of the cloud is actually, well, that's the illustration of the backend. The whole context is running within certain security context, and all the execution and information processing is happening on the execution context, security context. We figured to have the scalability and kind of background processing that we focus on the service interface on very thin layer of information providers such as web servers and media streaming servers. All the information processing is happening on background. It's kind of queued in a queue storage. Then there will be processing that stores and retrieves things to the information storage that then can be served. So basically information storage is the master of the information. That's where the current active status of the system is, then, and it's just been served with the web servers to the user. Now, exactly the same image, when we swap in the actual names of the things on Windows Azure, and the image becomes like. So we have a web roles on the interface layer, worker roles on the processing layer, queue and blob storage on the queue part. We need blob storage on a atomic operational queue that can be kind of, we can guarantee the execution order, but any worker can grab it. And then blob storage for being the actual information storage that's being retrieved through the web roles to the users. So the building blocks actually consists of information model, which is it has much of similarity with class models and namespaces. Then the process model, that's a service method model basically with orchestration sequence, so it dictates the steps what the certain process does. Then there are ADM modules which will concretize these things to service interfaces. Basically, it's going to be it's already is a platform agnostic. It generates native code. It generates native class models that can be serialized to the storage. Well, mostly we use .NET on that side on Azure. And then it has native code execution sequence. And everything is explicitly defined, explicitly documented out of it. It's already tracked. It's completely auditable. And we'll show a demonstration of this later on when we show how you design software and actually develop software, running software with the system, with the ADM-driven and powered system with Visual Studio on Azure. This is a very brief example of information model. It's just a schema-defined XML, non-relational model, basically here hierarchical with the primitive and complex data within it. Then this is poor to see, but it's an operation model which has a specification, input parameters, execution sequence, possibly return value. So the service operations are what you can think of as a services, with what we described a bit before. Okay, then the last part of the logical architecture, master information management. So when we have now defined or described a way to model information, although pretty high-end manner, we dive better on the part 2 on it. We spend some time to explain how we are not having relations and how and why it's a good thing. So we recognize the master of any information in the system. All the updates go to the master first. Any concurrency kind of the system that we are updating the latest data is checked against the master. Then from the master we are populating the whole information structure with the subscriptions and monitoring. So we kind of let the information flow update itself once updating the master. Evaluation chains. I'll soon show you the image to give better illustration. But basically, when we have cross-related information, we need to guarantee, or we better guarantee, that we only evaluate the things in the most efficient manner, so that we don't re-evaluate the changes in random order, so that we need to evaluate same object multiple times when we have actually evaluated it too early. So series of updates need to happen in an atomic sequence so that we can guarantee the order. When we do this, it scales really well. Although it is atomic, it's still because the security context size is relatively small, and it kind of makes the boundary of atomic operation relatively small. And this whole structure replaces traditional relations completely. So information is complete at every relevant stage. An illustration of it would be something that where we have an invoice presented to the user on a report or even as a letter or through the interface, that's actually consisting of atomic details of the smallest scale so that it can be backtracked and explain to the user of why there are certain amounts of CPU cycles, for instance, from the Azure or storage transactions in the system. And I'll show better how this flow happens on the running system. But basically, in the chain, we have multiple kind of duplicates of the same information, where the relevant part is actually the atomic ones in the beginning with, then flow parts in the middle are not so relevant until the fact that the invoice, of course, needs all that information to calculate the summaries to the user. And this whole chain is updated in one atomic kind of processing. All the updates can happen in the objects while the evaluation is done. So we kind of guarantee that the updates, or not guarantee, but we allow the updates to come in even during the evaluation, but we guarantee that we re-evaluate the whole package after the complete evaluation cycle if there are any updates. And those two parts kind of allow us still to guarantee the consistency of information, because the last part, the user interface focused information, the invoice summary container, the lowest one, the blue one before the actual UI, we can always kind of control when that one is updated, or we can have in our information models the ones that we know that they are not directly updated but only as resulting of evaluating the whole information flow, which means that when we take a look of this atomic system and see that there are no pending updates at that time, then we know that the system is at consistent state on that object. Even though the next second there pops in few updates and kind of invalidate the lower level objects, we still know that the one when we are holding the lock, the summary one, is at consistent state. Okay, that's for the summary of before diving to the demos. I'll now demo have a separate video for the actual platform executing, and then the part 2 is going to have a separate video of its own with the demo. Thanks for listening for the first part, and look for the same playlists of our demo videos for the actual demos and the part 2. Thanks for listening.